Okay, good morning everyone. So today we'll spend most of the time talking about the phase structure in the quark mass mu squared space. So I put mu squared because we also consider negative mu squared, so imaginary chemical potential. And so I'm just writing this every time, so it appears in the lectures on YouTube. So it's the same reference, and we're now in section 7 of these notes. So let me briefly summarize what we saw yesterday. So we looked at the Columbia plot. And what the Columbia plot gives you is the order of the phase transition, the thermal phase transition. For different quark masses. And so if we take the up and the down quark degenerate and the strange quark different, then we have two directions here. Here is on the horizontal axis we put the light quark mass, and we allow it to vary between 0 and infinity. And in the vertical axis we put a strange quark mass, and again it can vary between 0 and infinity. And we've seen that there are two regions that we understand. One is the region for very light quarks. So here the transition is first order, and this region has to do with chiral symmetry. And then we have the region for heavy quarks, where again it's first order. This point here would be the pure gauge theory. And this has to do with Z3, or the center symmetry. And in between it's a crossover, so these are lines, these are second order lines here, where the phase transition is second order, and in most of the plane it's a crossover. And we know that the physical point is in the crossover region. So that summarizes the nature of the phase transition at zero chemical potential. Are there any questions about this plot? Yeah.
So in the previous lecture, we said the Polyakov loop is somehow connected with the confinement.
Mm-hmm.
We didn't really go into detail. What does that mean?
Well, okay. So now let's come to the Polyakov. So then let's talk about the center symmetry, and then we'll naturally come to the Polyakov loop. So then we saw that in pure gauge theory, there is a symmetry which amount to multiplying the links in the temporal direction, say from x to x plus 4, with a simple phase vector, z to the k times u, where z is a multiple of 2 pi I divided by the number of colors, so 3, if I choose 3. And we said that this is we saw that the action is invariant as Young-Mills, and the measure are both invariant. And so this is a symmetry of the theory. But then indeed we introduce a Polyakov loop, which is a product of all the links in the temporal direction in the temporal direction. And this one is not invariant, because if I multiply a link at a given time slice, so this is at a time slice, then this Polyakov loop will transform by this phase vector, so it will not be invariant. And then we made a connection with confinement indeed, by saying, well, actually the Polyakov loop, if it's, it's all the temporal links, multiplied, going from 0 up to the end of the lattice, which is 1 over the temperature, that actually is the world line of a static quark. So, a lighter quark would hop around, say, but if the quark is infinitely heavy, it just sits here at lattice side x, spatial x, and it just stays at the same side, so that's an infinitely heavy quark. So it's the world line of a static quark. Is that part is clear? And then we made a connection with confinement by saying, now suppose we have two static quarks, and I want to compute the correlator, how they are correlated, say a quark and an anti-quark, at two different space points x and y. And if this is in the Young-Mills theory. And so I can associate a free energy with this particular configuration. So I can say, well, this is some kind of correlator, and I'm calling the way this depends on the distance. I call this the free energy. So this would be the free energy of this quark-anti-quark pair. And then I can take the situation, let's go to this board, where I'm taking x, the distance between x and y, to be very large. And in other words, if I take this distance very large, I'm separating the quark and anti-quark completely. But if I have confinement, I shouldn't be able to separate them. It will cost an infinite energy. So if the theory is confining, this separation should cost an infinite amount of energy. So this F will go to infinity, and so this correlator in a confining theory will go to 0 when the distance between the quark and the anti-quark goes to infinity. And then the final step is that actually if I pull these very far apart, there is these quark and anti-quark, they essentially become decorrelated. So it's like having a quark here and a quark somewhere else. So this actually becomes equal to the product of the individual expectation values, like this. And this is just the product of the expectation of the Polyakov loop, absolute value squared. And so when the free energy goes to infinity, this expectation value goes to 0. And so all of this, so in a confining theory, then the conclusion is that the expectation value of the Polyakov loop is 0. Yeah. On the other hand, if the theory is not confining, there's quite an easy argument to see that the expectation value is not 0, so not confining. So we can think about perturbative QCD, perturbative theory. The gauge potentials will be, say, small, and so the Polyakov loop, which is like a product of the gauge potentials along the temporal direction, say like this, will be close to 1, because I have essentially a 0 in the exponential. I should take the trace. Huh? Yeah, so there's a trace here So these are still SU3 matrices, so I'm tracing over the SU3 matrices. So this is a 1, as not a matrix 1, but a real 1. And so the expectation value of the Polyakov loop in a deconfined phase, say, is not equal to 0, and is, say, order 1. And so what we see then is that it is an order parameter because we have an exact symmetry, which is this center symmetry, where we multiply the links with an element of the center. It's a symmetry of the action and the measure, so it's a symmetry of the path integral. But the Polyakov loop is not invariant under this symmetry, so it's an order parameter. And there are clearly two phases, namely one phase where the expectation value is 0, and one phase where the expectation value is non-zero. So it's like magnetization. It's very similar to that. So that was roughly what we did yesterday. Are there any further questions about this? Okay, so this was all done with without quarks. So this was done in a pure gauge theory, because in a theory without quarks, it is indeed a symmetry of the action and the path integral. But if I now include quarks, I have terms which are of the order psi x, u 4, x, gamma 4. Let's put the chemical potential in here as well. Psi x plus 4, something like this. And if I now do this center transformation, the fermionic action is not invariant because I multiply this link with one factor of z, or z to the power k, and is not compensated by something else. So this is not invariant on the center symmetry. And so now the theory is, so the symmetry is not potentially spontaneously broken, but it's explicitly broken. And actually that means that in this Columbia plot here, this region is covered by this exact symmetry, which then still is relevant for very heavy quarks, where the symmetry is only broken a little bit. But in this main region of this mass diagram, there is no symmetry really that you can use to say whether the theory is, whether there's an order parameter. And actually one of the one research program that people are carrying out is to somehow identify an order parameter that can tell you something about the phase transition. But it won't be this one.
What about, is there another continuum theory of the center symmetry?
Yes, yeah. So you can define this all in the continuum. Yeah, so you don't do it on a given time slice, but you... it is Euclidean somehow. It's very hard to imagine it being Minkowski because it has to do with the fourth direction. But you can just do it also in the continuum, yeah. I wouldn't... Well, yeah, you basically do it in terms of Wilson lines and Polyakov loops, which also can be defined in the continuum. Yeah, good question though. So typically, actually the center symmetry, I have to think now. So if you do perturbative theory, perturbative calculations, the center symmetry is quite difficult to realize because in perturbative theories you typically have work in this area. So, but there are, say, perturbative studies that explicitly try to implement the center symmetry as a symmetry. Yeah. In a formal way, yeah. And I'm thinking actually of effective field theory ways where you do dimensional reduction and you still somehow have the center symmetry. That's what's in my mind. Yeah.
There are a lot of effective theories using Polyakov loop as order parameters.
Mm-hmm.
Are they them wrong or?
No, they're fine. No, they're fine. So effectively, it's still okay. So in an effective theory, so what does it mean, effective theory? You come up with some kind of Ginzburg-Landau model or a potential. So let's call it some potential, which is a function of, say, the Polyakov loop and maybe the conjugate Polyakov loop, something like this. And like in a la Ginzburg-Landau, you can have a potential, I mean very schematically, I'm not putting any axis labels, you can have a potential like this, which would have a first order transition, or if you change the parameters in this potential, maybe you have something like this, which no longer has a first order transition. So you can study it in an effective model, and by changing the parameters of this effective potential or effective theory, you can go between these two possibilities, first order transition, crossover, just by doing that. Yeah, good question. Okay, so now with fermions is no longer invariant, but actually we can see already something here. So that's why I put the chemical potential here. Suppose now I make the chemical potential imaginary. So let's do that. Let's put an I here. And I have this phase that I put in there, this z, and I multiply this link here with a phase vector z, which is e to the 2 pi I over n. And you can see that actually this phase here goes exponential times 2 pi over n, and also the chemical potential appears like this. So you can actually already see that somehow this phase that is picked up by the center transformation can be compensated by or absorbed in the chemical potential, provided it is imaginary. So they appear in exactly the same way. So we can make this a little bit more precise, and then have a, where is the thing? Does anybody see this one? Is this it? I thought this was candy. So now let's reconsider this center transformations when there is an imaginary chemical potential and see what happens. So how are we going to do this? So now with imaginary chemical potential, so I'm going to do it in two steps or two conditions. Basically, one is we put all the chemical potential dependence in the final time slice, and this is possible. We did this field redefinition where we transformed the chemical potential away from all the links, except it appeared at the end when you do the boundary condition, when you close the time circle, imaginary time circle. So put all mu I dependence in the final time slice. So then I have the dependencies of the form e to the mu I over t, or times n tau, because it's all these factors accumulate there. And then we also do perform the center transformation also on the final time slice. So I have there a factor z to the k, which is equal to e to the 2 pi I k over n, where n is the number of colors. So these two then naturally combine because so I put this in this chemical potential dependence in the final time slice. I multiply the links in the final time slice with this phase vector, and they exactly appear. So the natural combination to appear then is that k e to the I mu I over t. And so that's the exponent of I times mu I over t plus 2 pi k over n. So this is the natural combination arising in this case. And now you can see what I just hinted at. If you would do a center transformation, you can actually absorb the effect of the transformation in the chemical potential, in the imaginary chemical potential. So you can undo it. And so in other words, center symmetry is again a symmetry of the theory, provided I change the imaginary chemical potential. And so this is called Weiss symmetry, named after the people who first wrote it down. And it basically says that the partition function as a function of mu over t is actually periodic, so it's a function of mu over t plus 2 pi I k over n. So there's a new periodicity. Periodic in mu I. So if I go to imaginary mu, I have this periodicity, and this will show up in the phase diagram now. So that's quite interesting. In addition, we still have reflection symmetry. So Z minus mu over t is Z mu over t. So it's still even. And so if I think about, say, t mu I now, so I now look at the phase structure in the imaginary chemical potential dependence, then it's even. So this is symmetric, reflection invariant, but then there is this periodicity in the imaginary direction with 2 pi over n, and so there is periodicity on both sides here. So this is 0, and this is pi over n. Let's put this over t, and this is minus pi over n. So in the imaginary chemical potential direction, there is this periodicity where the extent here is 2 pi over n, and then this interval is repeated. In a way, this is not a surprise because there are phases here, so this periodicity comes out quite naturally. However, there is an effect on under this symmetry. Namely, if we go back to the Polyakov loop, and let's say the Polyakov loop, the expectation value of the Polyakov loop is 1. Suppose it's 1, so it's very high temperature, and we're in the deconfined phase. Now I can multiply it, and let's specialize now to n equals 3, so to QCD. Then I have 1, I have z, which is e to the 2 pi I over 3. I have z squared, which is e to the 4 pi I over 3. And I have z cubed, which is again 1. So I have 3 different phases, or 2 non-trivial phases, and one is just the identity. And if I do the center transformation, P, so I multiply this with Z, it actually does rotate. It goes to e to the 2 pi I over 3. So it's no longer, so in other words, if I increase, do the center transformation, or in other words, if I increase the chemical potential, because they are the same, both the center transformation and the imaginary chemical potential have the same effect, I change the phase of the Polyakov loop to 2 pi I over 3. And if I apply another factor of z, it will go to e to the 4 pi I over 3. And so this this structure by either doing a center transformation or increasing the imaginary chemical potential leads to the fact that this Polyakov loop has these 3 possible directions. So in the complex, say, Polyakov loop plane, we can either have 1, we can have z, or we can have z squared. So these are 3 faces with length 1, and they point in either the one direction, an angle of 120 degrees, an angle of 240 degrees. Now that's exactly what happens in this diagram here, because if I change the imaginary chemical potential, I'm actually cycling through these phases in the Polyakov loop because these two appear in this combination. And so if the expectation value of the Polyakov loop is, say, 1 in absence of chemical potential, so it points, say, in this direction, if I then go to higher values of imaginary chemical potential, I'm effectively doing a center transformation, and so the expectation value will point in this direction. So I'm reaching this step. And if I again cross a boundary, it's another power of 2 pi over 3, and the Polyakov loop points in this direction. So these, even though it's a periodicity, these 3 regions, or these different segments here, are actually separated by rotating the Polyakov loop through the 3 possible directions. Yeah? So in other words to say is that at 0 mu, the preferred direction of the Polyakov loop is 1, but at, say, mu I is 2 pi over 3, the preferred direction is z, and at 4 pi over 3, the preferred direction is z squared. So this is how this Polyakov loop rotates through these areas. Now this is only relevant, so when is this relevant, this analysis? When the Polyakov loop actually has an expectation value, because I'm multiplying the expectation value by a phase here. So this analysis is relevant when the Polyakov loop is non-zero, so in the deconfined phase. Because I'm looking at a situation that the Polyakov loop expectation value is not equal to 0. This part of the lecture is probably the most complicated one. So, although you should really always say to students that this part is not complicated, otherwise you are biased. Okay, so this, let's finish this argument and then I'll stop for questions. So this is relevant in the deconfined phase, when the expectation value of the Polyakov loop is non-zero. In the confined phase, the expectation value is 0, and so this has no effect. So, in other words, if I change the chemical potential, it won't affect this structure. So, effectively then, we have this phase diagram in the mu I plane over T. So this is minus pi over 3, pi over 3, 3 pi over 3, 5 pi over 3. And so we have these boundaries. So at high temperature, this is relevant. Okay, let's first look at the, so at high temperature this is relevant, so in the deconfined phase. At low temperature it's not. And so there is a a critical temperature here, say. So let's call this Tc, where the phase transition happens. So it's relevant in this this area here, above this line here. How does Tc depend on mu, imaginary mu? Well, we saw that for real mu, the phase boundary curves downward. And so for imaginary mu, so it's a function of mu squared, so this will be Tc at 0, 1 minus mu I squared with some coefficient. So it will, it's minus for real mu, so it's plus for imaginary mu. So this boundary here will go upwards. Something like this. And then it's periodic, so we can continue this thermal transition in a periodic fashion. So this is confined, deconfined. And then in the deconfined phase, this Polyakov loop is rotating through these different directions. And so here I actually have a transition where the Polyakov loop changes its orientation. So in this low temperature phase here, say, the Polyakov loop is 0. In the high temperature phase here, it's non-zero. And it points in these different directions. Exactly, that's the last bit of the argument now. The Polyakov loop is now again an order parameter because it changes, drastically or whatever. It changes sharply, indeed, as you said, from 1 to e to the 2 pi I over 3 to e to the 4 pi I over 3. So there's a strong, it's an order parameter with a strong change in value. And so these vertical lines here, when you go from one region of mu I to another region, are actually first order lines. So it's a first order phase transition at mu I over t is 2n plus 1 times k over 2 pi, is that right? So k, 3 pi over 3. So it's, I know, that's what happens when you improvise. Is this right? So n equals 0 is pi over 3, n equals 1 is pi, and n equals 2 is phi. Yeah. So at these values of mu I, so multiples of, basically multiples of 2 pi over 3, the Polyakov loop changes the direction, and so there's a first order transition, and it's again an order parameter for this transition. So that's quite interesting. So with imaginary mu, in the presence of quarks, we again have found a symmetry with a phase, with an order parameter and a first order transition. Yeah.
I didn't get why the frontier from zero value of Polyakov loop has this structure.
This shape.
The shape,
Like this one here. Yeah. Okay, so that's a good question. So for real mu, we are used to the fact that the phase boundary curves like this, curves down. And that's indeed what has been done, has been established with lattice simulation, say that if I look at Tc as a function of mu, I find, okay, is Tc at 0 mu, and then to get the dimension right, say 1 minus a number times mu over t squared, and then order mu over t to the power of 4. So this coefficient here, if I put a minus sign here, this coefficient is positive. And so for real mu, the phase boundary curves downward. Yeah? So now I do consider imaginary mu, so now I do an analytic continuation. And so the critical temperature as a function of mu I will be the same. I mean, I have this expanded version, 1. But if I change mu to I times mu, I get I squared as plus. So it becomes plus times mu I over T squared, like this. So I get a plus here. So minus mu squared goes to plus mu I squared with the same coefficient, because it's an analytic function of mu, or mu squared. So with the same coefficient, and that means that if now in the mu I direction, the thermal transition is this value plus something which goes with mu squared, so it goes up quadratically. And that's what I've drawn up there, so it's a parabola, the first approximation.
Yes, but there we put mu I over T, not mu I in the upper part.
Yeah, that's a very good point as well. So I always plot, well, there I put mu I over T, because then I have just pi over 3 there, basically. But indeed, if T is changing, and I plot it as a function of mu I over T, sometimes you have to draw these lines then with an angle, you know. So the point is that these lines, the vertical lines, happen at fixed mu I over T. And this quadratic dependence here, well, it's also mu I over T, really. Huh? Well, so this depends on how I define this, really. So I made it dimensionless by dividing by T. It cannot depend on the temperature. So, okay, so a better way would be to normalize it with Tc at 0, indeed, yeah. So sometimes, so this, okay, good point. So this graph is ideally drawn as a function of T and mu I, whereas that graph is ideally drawn as a function of T and mu I over T. So you have to do the transformation in your head. Yeah. Yeah. Yeah, indeed. This cannot depend on T. So, okay, other questions?
Excuse me, the fact that you say that the zero chemical combination, the confirmed expectation value is the one which is real among the three. It is due to the fact that you want to match with the decoupling theory at the real temperature.
Yeah, that's one way to argue that indeed at recoupling theory, the field strength, the field potentials are small, so P is 1 is preferred. Do it in a more effective model calculation, I guess, was saying that the quarks are like, say, external magnetization in the Ising model type structure, so they prefer that, you know, so they prefer that direction. So it's like a symmetry breaking term. It's a bit hard to see that, but it's like an explicit symmetry breaking term which turns it into that direction and not into another one. But indeed, the high temperature connection is probably the easiest to see, yeah. Okay, so let's now tie these things together. So we have the phase diagram as a function of real mu. We have the phase structure as a function of imaginary mu. And so I can obviously combine them by plotting it as a function of mu squared. So we can combine these two phase diagrams, say, in a T mu squared plane, because positive mu squared corresponds to real mu, whereas negative mu squared corresponds to imaginary mu. So I can combine these results. So let's so let's do that, and then so T mu squared. So as a function of mu squared, the thermal transition is a function of mu squared for small mu. So I get a straight line here through 0, like this. But then if I go to negative mu squared, so to imaginary mu, I have this special value here, up there, which is pi. So now I'm make sure I multiply it in the right way. So this is a straight line as a function of mu. So I have this Roberge-Weiss line here coming down from infinity, where the Polyakov loop changes value. And so the natural way to do, the natural connection to make, is to tie up these two lines here. Let me draw it a little bit flatter into this point here. And then it repeats itself because it's periodic. Yeah, so here I have a first order line, because this is where the Polyakov loop changes its direction. Down here I'm in the confined phase. Nothing happens. And then this is the thermal transition. Both for real mu and imaginary mu. So this is how we can tie these lines together. Then what happens here, nobody knows. That's very hard to guess from this argument, because we're now focusing on this part of the phase diagram, so small mu squared and negative mu squared. So this is the phase diagram in the mu squared, T mu squared plane. So this first order transition here ends, as we said here, because if P is, if the expectation value of the Polyakov loop is 0, there's no longer this first order transition, so there's an endpoint here. And this endpoint is really there. You can, as we've just done, we've argued it analytically. And so this one is called the Roberge-Weiss endpoint. Okay, any questions about this? The order of the phase transition? That's a very good question, which we're going to address now. So this depends on whether the thermal transition here is first order or a crossover. So we saw this. So now we go back to the Columbia plot, and we make this graph more realistic by saying, okay, for heavy quarks, this is a first order line. For very light quarks, this is a first order line. But for intermediate masses, it's a crossover. And so that will then impact this order of this, the property of that Roberge-Weiss endpoint indeed. So very good point. So let's go back now to the Columbia plot. So let me again draw it here. And for simplicity, let's take the case of 3 degenerate flavors. So I'm taking the case that the 3 quark masses are equal. And so then I'm cutting a line through this plot like this here. So if I do this, and if I start with 0 masses, 0 quark mass, I have a first order region, second order, and second order line, second order point, crossover, second order, first order. And let's now see what the impact is on this diagram here. So the first possibility is, so NF equals 3 quarks either very heavy or very light. If that's the case, then I'm in the region of the first order transition. So let me put that here. So if I have a first order thermal transition, then this will extend to non-zero mu as well. So then it's very reasonable to assume, that basically it's everywhere the transition is first order. So the thermal transition is first order, the Roberge-Weiss transition is first order, and so all the first order. If that's the case, then this Roberge-Weiss endpoint is a line where three first order lines come together. And if three first order lines come together, this is a triple point. So three first order lines meet. So that's the situation with very heavy quarks or very light quarks. Now I can increase the quark mass or reduce the quark mass to go to the crossover region so that the phase transition becomes a crossover, so intermediate values. Of the quark mass. The thermal transition is a crossover now, so again it's a function of mu. And so let's denote it with a dotted line here. So this is a crossover. Now then, again, there are some possibilities. Either this crossover turns into a first order transition, which is something we expect here. For real mu, this is something we expect because this is the critical endpoint. So this will be the critical endpoint at real mu. The same might happen at imaginary mu, so there might also be a critical endpoint in this side where the line turns into a first order line. So this is also a critical endpoint, but for negative mu squared, so for imaginary mu. So that is logically, that's a possibility. And in this case, the Roberge-Weiss point is still a triple point because I still got three first order transitions coming together there. And we can go further, we can reduce the quark mass or increase the quark mass still further so that this crossover region widens. And so the third possibility is further change the quark masses. And if I do that, I can end up with this following situation where the thermal transition is crossover all the way. And so we have thermal crossover for all values of mu. And in that case, this Roberge-Weiss point is a critical endpoint because it's the end of a line of first order phase transitions. So this is critical endpoint, which is second order. So it's the end of line, end of first order line. And of course, something might happen on this side. There might be a critical endpoint here or not, but that we can't tell from this argument. So these are the three logical situations. Either the thermal transition is first order for all. Yeah.
In the second case,
Yeah.
is the argument for the critical endpoint in the negative these were just symmetry or something more?
Well, if a first order line ends somewhere, it will end on a second order point and would then turn into a crossover. So that's kind of from a theory of phase transitions, say. So that's a general statement, and that's it really. So either the line ends somewhere here, or it just ends exactly at the end of this line. Yeah. So logically, these are the three possibilities, and of course, this can be studied at imaginary mu. So the nature of this point can be studied in detail. So this motivates studies of the Roberge-Weiss point. So its location is at say Tc, and so at mu, say at mu I is pi over 3 times T Roberge-Weiss. And this is at imaginary mu, so this can be done on the lattice. And so there's been quite a number of lattice studies, especially in Italy, actually, on this. And this simulation, in a way, okay, they're difficult simulations, but they're quite straightforward because you fix mu to be pi over 3, and then you vary the temperature, and you see what happens, when you have a critical point here or not. So you know exactly what to do, basically. You just do a temperature, so rather than doing a temperature scan here, you do a temperature scan here, and you find properties of this critical endpoint. Okay, let's see. Let's have a few questions, if there are questions. And then we'll have a short break now, because now we're going to extend it to have even go to different spaces, different planes. Yeah. So I have a 5-minute break for coffee. So we have this Roberge-Weiss point. So we call the temperature T Roberge-Weiss. And we've seen that for light and heavy quarks, is first order, and for intermediate quarks, it is a second order endpoint. And so I can actually now go to a different plane, namely to the plane of temperature quark mass, to draw this information. So here I put the quark mass, and suppose I'm in the 3-flavor case, so the 3 flavors are degenerate. And here I put this temperature of the Roberge-Weiss endpoint. So there's one thing I haven't told you yet, and that's namely what is actually the temperature where the Roberge-Weiss point sits, because I've just always drawn it as this vertical line here. But you may know that in pure gauge theory, the temperature of the transition is about 240 MeV, if I remember correctly. And for physical quarks, it's about 155 MeV. So one thing to know is that Tc depends on the quark mass. And so if the quark mass goes to infinity is, Claudio, is it 240 or 220 or 240? 240. About 240 MeV, whereas for physical quark masses, it's about 155 MeV. So in other words, the critical temperature goes down when the quarks get lighter, and in the same way, the temperature where the Roberge-Weiss point sits is lower for light quarks. So roughly, say the Roberge-Weiss, and the critical temperature where the Roberge-Weiss point sits is high for heavy quarks and lower for light quarks. And then I can implement this information here, namely that for very light quarks or very heavy quarks, it's a first order transition. Oops, this is very nice chalk to write, but the sound is less present. So for very light quarks and heavy quarks, it's a first order transition. So the Roberge-Weiss point is first order, whereas for intermediate quarks, it was this critical endpoint, and it's a second order line. So here, in between, it's second order line. Second order transition. So we're now in a different plane. We're now in the plane of critical temperature quark mass. And so in this plane we have either a first order transition or a second order transition. And again now we have 2 points here where a first order transition meets a second order transition, just like in this endpoint here, but now it's, as I emphasize, it's in a different plane. So again, I have 2 critical points here, where second order line meets a first order line. So let me see where I would draw that. This one here and this one here are tricritical points. Yeah, so this is the in this particular plane, this is the structure of the phase transition. And let's say this is for the case NF equals 3. Are there any questions? So this is now. So we made a change from the T mu phase diagram, or T mu squared phase diagram. We went to the critical temperature quark mass plane. Yeah? And now we're going to incorporate this information in the Columbia plot. So we're going to build now a quite more structure basically. So let's do that. So let's go back to the Columbia plot now. So if you remember, this was the Columbia plot at 0 mu. This was just the order of the thermal transition. So in the same way, I can study the Columbia plot not at mu equals 0, but at mu equals, imaginary mu equals pi over 3. So I can look at the nature of the phase transition at mu I is pi over 3t. And I'm looking at the transition, so this is really the Roberge-Weiss temperature. Yeah, so I'm looking at the properties of the thermal transition, not at 0 mu, but at the Roberge-Weiss temperature at imaginary mu. Actually, we've done one of these cases here, because this was the case NF equals 3. So this is a line through this Columbia plot here. And so roughly, we expect that it looks like this, M up, down, and strange. And we kind of expect, again, that there is a first order region for very light quarks and very heavy quarks, just based on the analysis we've just done. But the region in the middle now, so as you remember, the Roberge-Weiss point is always either a triple point or a critical endpoint. And it's a critical endpoint for intermediate quark masses, and it's then a second order transition. So whereas in the Columbia plot for 0 mu, this was a crossover, this is now actually a second order transition. So this is where the Roberge-Weiss point is a critical endpoint. And what this plot shows here is the actual temperature of the Roberge-Weiss point for the 3-flavor case. So essentially on this diagonal line, we have first order, second order, first order, which is exactly this region here, first order, second order, first order. And where the first and the second order meet, there is a tricritical point. And so these dashed lines here are tricritical lines. So this is kind of the most complicated conceptual step. So to go from the phase diagram, the T-mu plane, to these either quark mass planes or critical temperature planes. So, are there any questions about this? Yeah.
Where's the physical point?
Good question. So the physical point at 0 mu is here. Now, the physical point for imaginary mu doesn't really exist because nature doesn't have imaginary mu. But if I would draw the point at the same quark masses, it is actually also roughly here. So it's in the, I was just checking this with Claudio, who's done the calculations on this, for this. It's actually in the second order region. So in other words, for physical quark masses, the Roberge-Weiss point is a critical endpoint. Yeah. Other questions? Yeah.
So if in lattice simulations we find that so that this RW point is critical endpoint, that would automatically imply that for real chemical potentials there is also a critical endpoint, right? That it exists.
No, actually, I would say the reasoning is the other way around, but that's exactly what we're coming to now. If this is a critical endpoint, so it's on this side of this tricritical line, it most likely implies that for 0 mu, the transition is a crossover. And the connection then with a possible critical endpoint for real mu, so for positive mu squared, is actually not clear at all, say, let's put it like this. So the real, so we'll do that now. We'll take it as it goes, and then we'll come to your remark. Yeah. Okay, so now I have two of these planes here in the space of the quark masses. One at mu, so one at this. So this one is at mu squared equals minus pi over 3 t Roberge-Weiss squared, and we have the plane here at mu equals 0. And so we combine them in a three-dimensional plot by also including now an axis which is mu squared. So if let's draw a vertical axis here, and let's say this vertical axis is mu squared. And so now I'm going to do three-dimensional drawings, and I teach first-year mechanics, and it always goes very wrong. So let's attempt three-dimensional drawings. So I'm gonna plot this quark mass plot here, m up, down, ms at 0 mu. So that's this plot here. So that's the Columbia plot. And so we know there is a first order region for light quarks and for heavy quarks. And in the middle there's a crossover. So that's the Columbia plot. And we have this plot here for the special value of mu, which corresponds to the Roberge-Weiss point. So there's a similar plot here now, like this. And this plot is at minus this value, pi g Roberge-Weiss over 3 squared. And in this plot, we again have a first order region. These boundaries are not really known, so I'm just drawing them as one can. So first order, and second order here. Yeah, so I've now, well, I'll let you draw the picture first. So I've drawn now these two planes, both in the same, so the two quark mass planes are different values of the chemical potential. And now I can, of course, change the chemical potential, and like in the plot over here, I can study the property of the phase transition as a function of any mu squared, either negative mu squared or positive mu squared. So in other words, I can fill in the gaps in between here and basically connect all of these lines here like this. So I have a proper three-dimensional plot, and it's very suggestive then that, of course, these first order regions are connected by some kind of, well, this is now the difficult bit. So there's some kind of surface here which connects these first order lines here. So the way to look at this now is that I have now first order. So everything to the left in this corner is first order, and to the right is first order. And these first order regions are ended by second order surfaces. And in the middle then it's a crossover. Yeah. So it's quite an interesting graph. So let me try to draw it again without all the letters in between. So I'm going to copy this nice figure here. So this is minus pi over 3. So this is mu over t squared, 0 minus pi over 3 squared. And so I have two surfaces here. One is the surface in the heavy quark corner, like this. And the other surface is here in the light quark corner, like here. So this is the surface. 0, infinity, up, down, s from 0 to infinity. So in the three-dimensional space, then I have these second-order surface. I have a first-order region on the inside of these, well, on the right side or the left side of these surfaces, and crossover in between. So the region below 0 is accessible to simulations. The regions above is only accessible via Taylor series or something like that. And then to come back to your question about physical point. So the physical point stays roughly somewhere here in the crossover region, or in the critical endpoint region for at this special value of mu, but in the crossover region for all other chemical potentials. So so there is a crossover basically for all chemical potentials based on this, you know, in this range of values of chemical potential. So physical point, it's at the Weiss point, it's a critical endpoint, and for mu squared over t squared larger than minus pi over 3 squared, it's a crossover. Now, how could we make it into, how could it be a critical endpoint again? So how could we turn this transition from crossover into a critical endpoint for real mu? Well, one possibility would be that this surface here, so it becomes a critical endpoint if it's first order on this side, critical endpoint crossover. So, and here we have first order critical endpoint crossover. If this surface would somehow, for one reason or the other, bend backwards, say, and it would pierce through this surface again, so it appears on the inside of this surface here. So where the critical end, where this physical line goes through the surface, this surface is a second order surface, that will be the critical endpoint. So if it would happen to be that these simulations would have shown that the physical point is deeply inside this first order region for negative mu squared, like here, then it will be quite easy to say, okay, well, it goes through the second order surface there, so that is the critical endpoint. But as has happened, is not the case. Even for these negative mu squared values, it's a crossover, and this area is squeezed to the small quark corner. So in other words, it's actually really hard to learn something about the potential critical endpoint here from this kind of phase structure. It does not arise in this structure. So this is, I would say that's an open question. Whether there is a critical endpoint is an open question, and how it would be fitted into this kind of three-dimensional phase structure. One other comment which somebody remarked in the break. So when I said, okay, we can do the Taylor series and it's analytic in mu or in mu squared, of course there's a finite radius of convergence for this, and this radius convergence is limited by singularities in the mu squared plane. So we know for sure that the radius of convergence is limited by this Roberge-Weiss point. So that sets a maximum limit to the radius of convergence of the Taylor series. And so one can try just from the Taylor series around 0 to learn something about the nearest singularity, either this one or another one. But that actually needs quite a lot of terms in the Taylor series to really say something about that. So that hasn't been achieved yet. Any questions about, say, this diagram in particular? Okay. Well, we are not yet done, because we can do a little bit more. So there's one more step to take, which is actually quite interesting. I find the way critical phenomena in this lower part of this diagram impact the behavior at positive values of mu squared. So we'll do that now. So again, I'm going to take a cut through this three-dimensional space. So let's go back to this graph here, and let's consider again the three flavor case. So I'm going to go along this line here and just look at this two-dimensional plane for three flavors. So what does it look like? Something like this. This is the quark mass from 0 to infinity. And this is the, say, mu over t squared. This is 0. This is minus pi over 3 squared. And so if I go through this plane in this way, what do I encounter? I have this first order region for small quark masses and for large quark masses. So I have these lines here essentially like this. So these are these lines here on this surface. And so to the left and to the right is first order. In the middle, it's a crossover. And then these lines here, which separate, which are basically the surfaces here, these are the second order lines. And then on the bottom, it was second order as well. Huh? This is the Roberge-Weiss point, which is second order, and here are these critical points. Yeah, so this is just this a slice to this graph for three flavors. So this second order and tricritical. Now I can take this graph and let's rotate it by 90 degrees. And so if I do that, I get something like this, again as a function of mu over t squared, 0 minus pi over 3 squared. And so I've rotated over over 90 degrees, so now the quark mass is not on the horizontal axis but on the vertical axis. And if I rotate it and I look at, say, this one here, I start at minus pi over 3 squared. I have a tricritical point. So that's this point here. So that point corresponds to this point. And then I have this line coming out like this. So this line is equal to this line. And above the line is first order. Below the line is crossover. And the line itself is second order. Still with me? Now this is actually quite an interesting diagram. So we can call this line here, this second order line, is essentially a critical line. So let's call this line MC. So for critical, so that's the second order line in this plane of quark mass and chemical potential. So MC as a function of mu over t squared indicates the second order line. Now what's interesting is that this line actually starts at a tricritical point for this particular value of mu. So at mu over t squared is minus pi squared over 3 squared, it's a tricritical point. Now, and then the theory of phase transitions tells you that this line will satisfy something which is called tricritical scaling. So it has a certain form which depends on universality and not on details of the theory. So it's universal, which is what you have in phase transitions, basically. So the theory of phase transitions then tells us that this function m critical quark mass here is determined by what's called tricritical scaling. So if I denote, so the horizontal axis, the dependence is on mu over t squared. So I'm going to denote this with x equals mu over t squared. And the tricritical point is at this special value minus pi over 3 squared. So I'm going to call that x star is minus pi over 3 squared. Then tricritical scaling tells you that this function as a function of mu squared, so as a function of x, should scale with a certain power, namely, okay, it's the value at the critical point, at the tricritical point, and then in the vicinity of the tricritical point, it will behave as x minus x star to the power 2 over 5. So in other words, the curvature here, or the x dependence, this dependence here, is not arbitrary. It's actually determined by the scaling in the vicinity of this tricritical point. So it's not just any line basically here. So k depends on details, so it's not universal. But the power 2 over 5 is universal. Now that's actually extremely powerful because it tells us that this part of the phase diagram, where we have this surface separating the first order region from the crossover region, is actually a line here which is determined by this tricritical point, which is the Roberge-Weiss point here. So in other words, even though we introduce chemical potential, imaginary chemical potential as kind of a trick, the fact that there is a critical endpoint here for values of mu, and therefore a tricritical point in this larger space, determines the curvature of this surface, potentially even for positive mu squared, so for real mu squared. So that's extremely strong statement, I think. Now, can we test this, whether this is true? Unfortunately, of course, in QCD, it's really hard to do these simulations. So let me erase this one over here. So the question is tricritical scaling relevant for mu squared greater than 0, so for positive x in this scaling. Now, this has been studied in toy models or effective models. And the models that have been studied is either QCD with heavy quarks. Of course, I've given the reasoning for light quarks here in this service, but the same holds for heavy quarks and this service or this line. So you can investigate this side, the tricritical scaling on this side of the diagram. And it has been studied for so actually heavy quarks in the strong coupling expansion, so even a little bit further away from QCD. And in the Potts model. Potts model is an effective model for QCD with heavy quarks as well. Essentially there are 3 states like the Polyakov loop. And so in both of these theories, you can do simulations, in fact, for real mu and for imaginary mu. So the sign problem can be solved here. So you can do these simulations explicitly. And what you find that if you do the simulations, you find indeed a curve that looks like this. So let's say there are data points here. And when you draw this line from the tricritical scaling, then lo and behold, this line basically goes through the data points, or vice versa. Data point goes through this line. So in the lecture notes, there's some more detailed, well, it looks like this, but a bit more quantitative. So in other words, this tricritical scaling, which is impact for positive mu squared, so for real mu, has been, say, confirmed in these effective models. So that's quite nice. Now, ideally, we want to do this not for the heavy quark sector on this side, but we want to know it for the light quark sector on this side. But that is a major numerical simulation, partially because this surface actually is present for such light quarks that you need quarks which are lighter than in nature. So you're really pushing the boundaries of the computers and the algorithms to access this. So for QCD, you need simulations at quark masses which are lighter than the quark masses in nature. So, and that's a major undertaking to do that. But I think it's extremely interesting because, as I said, we introduced chemical potential, imaginary chemical potential as kind of a trick to just note, hey, the determinant is real. Let's just see what happens. But then actually in this extended space, you can see that it all hangs together and that even, this tricritical line of tricritical points here impacts the curvature of this surface when you go to real mu. So it's quite an interesting connection. Okay, any questions about this? This was the critical, the quark mass on the second order line. So it's the same plot as on the top there. Is that same plot as over there? But now with actual, real data points drawn in here. This is only for heavy quarks. So these simulations have only been, so this has been verified only for heavy quarks. Yeah. So for this side of the diagram here, so this line is that line, it's that line. Yeah. And we would like to do it for this line here, but that requires quarks lighter than in nature to simulate. So, yeah. Other comments, questions? Yeah.
How do we know the specific universal?
So this exponent here follows from, as I said, the theory of phase transitions in a very generic way. So this goes back to the 70s, basically, and tricritical scaling and renormalization group, and so this goes back to people like Widom and so on. So yeah, have to so beyond my knowledge. Yeah.
So when we have a second order phase transition, we also have other scales.
That's right. Yeah. So indeed. So this scaling is the scaling in this point, in this plane, basically. But in the T mu plane, mu squared plane, say this critical, suppose it's a second order critical endpoint, this Weiss point, that has its own scaling associated with this. So physical observables or susceptibilities or something like that at this critical endpoint will diverge in a certain way. So that's right. So there's also universal scaling attached to that, but in a different plane than that one. Yeah.
Is this one in Potts universality plus, right?
The Potts model and so on are, for heavy quarks, it's in the same universality class. Yeah, for heavy quarks, yeah. I think so, yeah. Now, these models are so simple. Well, this is not that simple, but this is so simple that you throw away most of the dynamics, but it should still capture some of the features. Yeah. Okay, so this was, if you have no more questions about this was all I want to say about this Columbia plot, order of the phase transition, imaginary mu. And so in the rest of the lectures, I want to go discuss solutions of the sign problem which go really which are more bolder, which go outside of kind of standard Monte Carlo methods. This has to do with how we generically really do. So we have a complex valued integral, And we would never imagine doing an integral with a complex function, analytic complex function by Monte Carlo. We would do something else. So the last section. I'll call it last section. So which says, let's say, take the complexity of the weight seriously. And so we're going to think about the path integral in complexified spaces. So and there are a number of approaches related to this. One is complex Langevin dynamics. And then we have something called the Lefschetz-Timbal. And we have something called holomorphic flow, anti-holomorphic flow. So these are approaches which are related one way or the other, because we're going to consider the path integral not as now a highly oscillatory function for on the real axis, so to speak, but we're going to go into the complex plane, which is very natural when you think about integrals with complex weights. It should be said none of these methods have really yet convincingly solved the sign problem in QCD. This one is the furthest along, but somehow the generic lessons are quite interesting again, because it shows you, well, so it's like an exercise in field theory, and go outside of your comfort zone essentially. So let's start with something very basic. So what's the main idea? So I have some probability weight. I'm just using one degree of freedom here. This is some complex function. So if I'm on the real axis, if I look at this function, the real part of this function as a function of the degree of freedom, so just one degree of freedom, it's potentially something like a highly oscillatory function, something like this. And suppose I'm, very stubborn, and I want to solve this, say the integral, so the partition function would be an integral over x of this complex weight. And suppose I'm very stubborn and I insist I want to solve this by Monte Carlo method, one way or the other. I have to do extremely precise sampling to take all these oscillations into account and get the right answer. So that's like very tedious. But what we'll argue soon is that actually, typically when you do these integrals, especially these zero-dimensional integrals, of course you don't do them on the real axis, but you go into the complex plane. So you do an analytic continuation. X goes to z is x plus iy. And maybe, lo and behold, in the complex plane, there is some nice probability distribution, P of x and y, which is real and positive. And so if I just, I'm less restrictive and I allow myself or the theory to go into the complex plane, I actually have a perfectly well-defined integral which I can solve with, say, a numerical integration or so. Now, this is not, so it may sound a bit vague, but this is, of course, something you know very well. So let's take a very simple example. So I'm writing it as if it is a past integral, but of course it's just a zero-dimensional integral. So it's just a Gaussian integral, shifted, and I put an I here, so there's a complex value there. And if I plot the real part of this e to the minus s, of course it's exactly what I just sketched, this e to the minus a half a x squared times the cosine of bx. So depending on my value of b, this will indeed be a highly oscillatory integral. So how would you do this integral if you wouldn't be thinking about numerical integration and whatnot? This integral here. Shift variables, exactly. So you would do it by completing the square. And if I complete the square, I effectively shift the, so I shift the variable to x goes to x, well, now I have to do it in my head, minus ib over a, something of this, that form. Looks fine to everyone. So in other words, I'm shifting the variable, but by doing the shift, I actually go into the complex plane. So, you know, it's a complex, b is, or I is complex here, so I go into the complex plane. But if I do that, so if I, let me try to draw this, to think what exactly I want to draw. Say x, y, so this is 0, this is on the real axis, but if I shift it over this amount, say b over a, I complete the square, and it actually becomes again minus a half a x prime squared, so it becomes a perfectly well-defined Gaussian integral, but into the complex plane. So I shifted the integral into the complex plane. Now, this is a completely logical thing to do. And so the question is, can we do this for field theories? And also, can we do it in a way that avoids importance sampling? At least in the most naive way. So that's the question. Now, the first approach which I'll use to illustrate is Langevin dynamics. And Langevin dynamics is very natural because so it's like Brownian motion. Let me see. So this part is more motivated by avoid importance sampling, actually. So let's consider Brownian motion. And I have some kind of equation, say x dot, dot is the time, minus ax plus eta. And everything depends on time. And the noise here is just some simple Gaussian noise, which is normalized in a certain way. Now, if you think about Brownian motion, what will happen is that this degree of freedom, this x, say it's the position of a particle, it gets kicked around by the noise, but there's also a drift term which extracts energy. The noise puts in the energy. So after some time, after a long time, so as t goes to infinity, this degree of freedom thermalizes. And the distribution is determined by, well, in this case by A and by the noise, but I've normalized the noise. So what we'll show maybe in this afternoon questions or maybe tomorrow is that if you solve this long enough, if you solve this Langevin equation and you average over the noise, then indeed the moments that you get are the correct ones. So the expectation value here would be, say, given by 1 over A, which is what you actually expect from this integral, basically. So here the idea is we don't do any importance sampling. We solve a Langevin type equation. We wait for the system to become thermalized, get into equilibrium. The noise is chosen so that it reaches the right temperature, so to speak. And the expectation values are then determined by the properties of this drift term in the noise. And if I choose everything like this with A here and a 2 here, I get exactly the right expectation value. But the important thing is that I have not used, so I can solve this numerically, say, but I have not used any form of importance sampling. So there might be a way that we can generalize this now to theories where the drift is complex, or I have a complex action problem without doing importance sampling. Okay, I'll stop here. Any further questions? So we'll come back to all of this tomorrow in much more detail.